Hello everyone, I am Fatma from Qatar University and today I will present our paper Sensor-Reactive UAV Search and Rescue Deep Reinforcement Learning. Now let's give a quick overview about our motivation. Search and rescue operations after disasters are often very dangerous, they are time critical, and it's very difficult even for the human responders. So the UAV will offer a promising solution because they can safely inspect the damaged structure from outside the building. However, the main challenge is that survival locations are completely unknown here. In a realistic deployment, the UAV does not know where the survivors are located and it can't rely on predefined maps. So instead, it must make the decision using only its sensor information that it will receive during the mission. Now let's go through the research gaps very quickly. So many existing methods are making assumptions that are very difficult to satisfy in a real disaster environments. For example, they often assume a prior maps or a known target distribution or even a centralized coordination between multiple agents. In addition, many approaches do not model the problem as a partially observable environment. Another limitation is that the generalization is rarely evaluated across different survival counts and disaster conditions. So these limitations have motivated our research question, which is, can a UAV learn to search reactively using only its sensor signals under partial observability? Now let's go quickly through our contributions. First, we formulate the UAV survival search as a POMDB using a four-dimensional observation space. And second, we develop a PPO-based sensor-reactive navigation that relies only on the on-port sensing information. And it uses a very lightweight network that is suitable for the deployment on the edge devices. And third, we perform a systematic evaluation across different survival counts and coverage densities so we can assess the generalization. Now that we have discussed the contribution, let's look at the environment that is used in this work. So our environment is represented by a 15 by 15 building grid. Within the environment, we define three high-risk zones where the survivors are most likely to be located. And the UAV will operate externally and it will perform a through-wall sensing. So the objective here is to locate all the survivals within a limited mission budget. The overall process is shown in the bottom of the slide, as you can see. So the survivals will generate sensor signals. The UAV will observe those signals and make a navigation decision. And by that, gradually, we will start to build a search path. We modeled the search task as a POMDB, a partially observable Markov decision process. So the state contains the UAV position, the hidden probability map, the visit information, and a set of active survivals. The most important thing here is that the full state is never available to the agent, as the UAV only receives the four main observations, which are its normalized X position, its normalized Y position, the visit count, and the sensor reading. As for the action space, the UAV can move in any of the 8 directions, and the reward function it encouraged like an efficient exploration and successful survival localization, while also discouraging inefficient behavior such as the excessive revisits, for example. At the bottom of the slides, we can also see the sensor model. So for the sensor model, for each survivor, we generate a probability map representing the likelihood of detecting the survival throughout the environment. And when the UAV moves to a specific location, we look up to the probability value at that location from every active survival probability map. And these values will be then averaged to produce a single sensor measurement. So as a result, the UAV will never see the survival location or the probability map itself. It only receives one sensor value that will indicate how promising its current location is. And that creates a partially observable setting where the navigation decision must be made using only the local sensor feedback. To learn an effective search policy, we use the PPO, Proximal Policy Optimization, because it provides stable learning, strong exploration capabilities, and performs well in partially observable environments. The policy network was intentionally made very lightweight. It have a simple multi-layer with 2 hidden layers of 64 neurons each, and it produces one of the 8 movement actions. The training was performed for 6 million time steps using 3,000 generated maps. The most important thing, the agent was trained on only 3 survivals. And before discussing the results, let me briefly explain how the sensor data and the evaluation scenarios were generated. So to generate a realistic sensor measurements, we first created 3,000 probability maps offline. We define 3 high-risk zones. It represents the damaged building regions. The survivals will be sampled within these regions and assigned a probability distribution. So the sensor reading will then be computed from these distributions at the UAV location. So it's important to note that the UAV never sees the probability map directly. It only receives the resulting sensor measurement. And now for the evaluation, we train using only 3 survivals, and then we test on larger survival counts and a different coverage densities for the high-risk zones. And then we compare the PPO against our baselines, which are the DQN, DRQN, and digesterone as an upper bound. So with all this setup established, now we can evaluate the performance of the learned policy. So now let's start with the results. So in this figure, we can see the PPO training process. On the left side, we observe a very steady increase in the reward throughout the training, which indicates a stable learning and convergence. And on the right side, we can see an example trajectory from the unseen environment. The UAV was successfully following the sensor information, and it was able to locate all the survivals, which shows us that the agent actually learns a meaningful sensor-reactive behavior rather than just moving randomly. After confirming a successful training, we now have to evaluate whether the policy will be able to generalize to more challenging situations. So in this experiment, the PPO is trained only on scenarios that have 3 survivals, and then we will evaluate it on a larger number of survival counts without any retraining. And the result shows a very strong generalization. The PPO is able to achieve 96 success rate when the number of survival increases to 5 and 84% success rate when it increases to 8. Even in the most difficult case with the 12 survivals, the PPO was still maintaining a very high survival found rate. So the most important thing here is that the PPO outperformed both the DQN and the DRQN throughout all the target counts, which indicates that the learned search strategy here transfers very well to a more complex environments. Now moving on to the next experiment, where we vary the how wide. So to summarize the key findings of these experiments, the PPO was successfully learning sensor-reactive navigation using only the onboard sensor feedback. The learned policy was able to generalize well to the unseen survival counts and coverage densities without any retraining. It consistently outperformed the DQN, the DRQN, while remaining very close to our upper bound. And finally, it achieved this performance while requiring fewer search steps than the learned baselines. So all these results suggest that the sensor-reactive UAV search is both feasible and it's effective for a real-world disaster response scenarios. And thank you everyone for attending.